Morning, everyone. I'm Abigail Price, and today I'll be presenting my thesis titled Design of an Efficient U.S. Shipyard Layout and Material Flow Using an Existing U.S. Shipyard Land Area. I'll begin with some acknowledgments of those who made this thesis possible. I'll start by thanking the following members of web faculty. First, Professor Golden, my principal advisor, for his advice, guidance, and resources, including a block breakdown necessary for this thesis. Next, I wish to thank Professor Gallagher, my reader, for providing additional resources, advice, and perspectives. Finally, I would like to thank Assistant Dean Harris, my editor, for his help with the written thesis document. Additionally, I would like to thank the following members of the industry, starting with Ian Bush from General Dynamics NASCO for providing the key block breakdown needed for my analysis and for taking the time to discuss my findings and give me feedback throughout this process. Next, I wish to thank Karen Miller from Commonwealth Shipyard for providing the final block breakdown and some crucial information for my analysis. Then I want to thank Jerry Steiner from General Dynamics Bath Iron Works for providing several resources for the background of this thesis. Finally, I'd like to thank General Dynamics NASCO for allowing me to use their shipyard as my test case. The outline of today's presentation is as follows. First, I'll discuss the background of this thesis, followed by my objective. I will then discuss the theory behind shipyards. Next, I'll take you through my procedure, which will lead to my results and conclusions. I'll then finally close by making my recommendations for future work. General Dynamics NASCO is a shipyard that I use as my test case. It is also the shipyard in which I worked as a freshman. It is located in San Diego, California, and is the only full-service shipyard on the west coast of the United States. This means it can handle both repair and new build work. It is also capable of producing both commercial and military vessels. However, I will be focusing on the new build and commercial aspect of the shipyard. Many years ago, it started as California Iron Works in 1905, and over the years, it has gone through many different expansions and updates as new technology became available. However, these expansions possibly created a suboptimal layout material flow of the yard that this thesis hopes to address. Here is a photograph of the yard from the waterfront, and here's an aerial view of the shipyard with the bounds of the shipyard outlined in red. The objective of my thesis is to explore possible layouts and material flows of a modern new build shipyard on an existing site that improves efficiency. That existing site is NASCO. There are many design decisions that need to be made when designing a shipyard. First, the shipyard needs to decide the size and types of ships to be built, because the construction process of a tanker is very different than the construction process of a yacht. Along with this, the rate of production, or how many ships per year they wish to build, is also important to determine the amount of space you're going to need for the facilities. There also needs to be block breakdowns of each ship or similar ships in order to determine the size of facilities needed. There needs to be a discussion of the material handling equipment like cranes and transporters that the shipyard used to move material throughout the yard. Along with this, the part production and assembly processes used to actually construct the ship will determine the type of facilities needed. Additionally, the shipyard needs to determine how much outfitting is going to be undertaken at the yard itself as opposed to an offsite facility or by a vendor. Control services are what makes sure that the ship that is designed is the ship that is actually produced, and the shipyard needs to determine what those will be. Additionally, the final decision needs to be made is what administration facilities are required to have the shipyard run smoothly. A shipyard layout describes where the shipyard facilities are in relation to each other, whereas the shipyard material flow describes the route that the raw material takes on its journey to become the final ship. There are many shipyard facilities, starting with the assembly lines. The assembly lines are the backbone of ship construction, and without them, the ship would simply be a pile of steel, and unfortunately, piles of steel are not well known for their ability to float. Assembly lines begin by shaping and creating plates, which then add structure to them to become sub-assemblies. These sub-assemblies are combined to become blocks. Those blocks become grand blocks, and those grand blocks become the final ship. Next are outfitting, and while this thesis focuses on steel throughput as opposed to outfitting, these outfitting facilities still need to be considered. There are many components to outfitting, such as those listed on the screen, and they are installed at various points in the process, which makes it difficult to determine how much space is required for them and where to allocate that space. As discussed previously, this may be completed off-site by either a shipyard-owned off-site facility or by a vendor. Every steel shipyard needs to have blasted paint facilities because paint protects the raw steel from the harsh green environment, and blasting repairs the steel to be painted. This is often a bottleneck in most shipyards because paint requires very specific conditions in order to dry, and throwing more labor at the paint will not make it dry any faster. This can cause delays in the future. Launch facilities take the ship from dry land and transfer them to the waterway. There are many different types, such as the sliding ways, side launching facilities, grading docks, and floating dry docks. Once the ship has been launched, it is moved to the pier. which is considered the simplest facility because the ship is already supporting itself at that point. However, it still needs to be stable enough and accessible for both cranes and workers to complete the final outfitting before sea trials. The final facility I'll discuss is block storage. As the name suggests, it's a facility that stores blocks. Specifically, it stores blocks that are unable to be moved along in the process because there's delay ahead of them. Being able to move finished blocks to the side allows blocks behind them to still be produced, even if there is a delay. And as most of you in this room know, shipyards always will have delays. To determine the layout of this new shipyard, I needed to take several steps. First, I sized the blocks according to the block breakdowns. Then, I arranged facilities to create a more ideal layout of General Dynamics NASCO, focusing on shorter travel distances to decrease transition times. Once that was created, I determined the number of man hours needed to both construct the blocks and transition zone from one workstation to the next. Using that information, I was able to determine the overall improvement of the layout. This shipyard is producing 3 representative vessels. First is the 185,000 deadweight ton tanker provided to me by NASCO. Next, it's a 3,500 TEU container ship provided to me by Philly Shipyard. And last is a 49,000 deadweight ton tanker provided to me by Webb Institute via Professor Golden. The blocks were sized against the maximum capacity of the blocks and tape facility currently at NASCO, which has a maximum block capacity of 52 by 52 by 30 feet. Therefore, the sizes on the screen show must fit within those bounds. Next, I had to determine the number of blocks and ground blocks to be transferred through the shipyard. This was a challenge as in the large tanker block breakdown, the total number of blocks was available. However, no ground block information was given. Similarly, or oppositely, for the other two, I was only given ground block information. Therefore, using a combination of both of those, I was able to determine a total number of blocks of 587 and a total number of ground blocks of 88. To make changes to this layout, I first need to understand the current layout, which is shown on the screen. It starts at the raw steel storage area where a rail line comes and transfers the raw steel. Then it moves to the steel prep facility before moving to the thin plate panel line and the sifter assembly area. We're moving to the block assembly lines. Then outfitting that needs to be done before blast and paint occurs. Then the blocks are blasted and painted before moving to the grand block staging area where the blocks are grand blocked. Then any pre-erection outfitting occurs before the blocks are erected onto either the sliding ways or the graving dock. Once the ships have been launched, they are moved to the outfitting pier for the final outfitting before sea trials. The first change I made was by moving the raw steel storage and thus the rail line to the south side of the yard to allow for the majority of the construction process to occur in the largest section of the yard. Thus, I moved the steel prep facility, the thin plate panel line, sifters plate assemblies, and the block assembly lanes to this area while also bringing them closer together to decrease the transition time between workstations. Then I moved block storage to either side of the lanes. The next major decision I made was by moving the launch facilities to the north side of the yard. I also made the decision to change the launch facilities from the 2 sliding ways and 1 graving dock to all 3 graving docks. While sliding ways are a traditional method of launch, these become problems when you're trying to align blocks on an incline. Thus, changing to a graving dock allows for the blocks to be aligned on level ground, which will increase efficiency. However, due to space reasons, NASCO will need to build out a little bit into the waterway to meet the mass of the graving docks. Then, I moved the blast and paint facilities and the outfitting lane to in between the block assembly lanes and the grand block staging area. Finally, next I moved the machine shop and the unit assembly building to a more central location of the yard so it can be accessed from every part of the yard. Last, I added additional block storage to the grand block staging area for any blocks that are not quite ready to be grand blocked. Next, I had the challenge of determining how many man hours it would take to construct these blocks. NASCO splits its stage of construction into 7 stages, and thus the data in the block breakdown was also split that way. Stage 1 is plate burning and prep. Stage 2 is stiffeners and sub-assemblies. Stage 3 is block assembly. Stage 4 is outfitting and blast and paint. Stage 5 is grand blocking, and Stage 6 is grand block erection. You notice that Stage 7 is missing because that is sea trials and is therefore not included in my analysis. The large tanker block breakdown contained bold information for stages 2, 3, 5, and 6. Therefore, the man hours were directly calculated using a factor of it taking roughly 5 minutes to weld 1 meter with setup included. This number was given to me by a weld engineer from Philly Shipyard. This factor was then multiplied by 5 in stage 5 And 8 in stage 6 to follow the 1-5-8 rule discussed by Ian Bush, who explains that it takes longer to weld the same distance the further the ship is in construction. To determine stages 1 and stage 4 is a little more difficult because there's no weld information given. For stage 1, it was assumed that the majority of the man hours would be in plate burning. I was given a plate burning rate of 50 parts per hour per burner with 5 burners, which correlates to a man hour total of 478. For stage 4, this was a little more difficult than that because it includes both bots of paint and outfitting, which is a very variable part of a shipyard. I used a distribution of man hours given to me in that block breakdown. And using stage 3 as a base, I was able to determine an estimate of stage 4. Moving on to the transitions, I was able to determine the differences between my new layout and the current layout for how long it would take to move blocks from one stage to the next. Because there's no concrete information given for a new shipyard, I approximated the time savings by using some real figures that NASCO gave me and interpolating based on improvements such as distance between workstations and by changing the launch method. This related to a total improvement of transition times of 35%. Putting this table together with the previous table, I was able to determine for this new shipyard for building all 3 ships that there would be an improvement of 9%. You'll note that the steelwork does not change as no manufacturing processes were changed in the course of this thesis. The new shipyard is as follows, starting with the raw steel storage in the south end yard as discussed previously, moving on to the block assembly lanes, then transfer to the glass and paint and outfitting, before getting moved to the ground block staging area where the ground blocks are finally erected and launched to the outfitting lanes at the south side of the yard. My conclusion is that General Dynamics NASCO's shipyard efficiency can be improved if they were able to start from a blank slate. I explored 2 different ways to do this, by optimizing material flow and by minimizing the distances between workstations. However, there are plenty more factors to work with in terms of improving efficiency. Some of my recommendations for future work is to first focus on repair as opposed to new build and see how the shipyard would change if that was the case. Next, in a similar vein, is focusing on outfitting as opposed to steel throughput, or in a combination of that with the new layout. Next is to use different manufacturing processes to see how that would affect efficiency. Finally, my last recommendation is to do this analysis again by using a different shipyard. My recommendation would be to be Philly Shipyard because they are currently undergoing a re-optimization process, and I'd be interested to see how a from-scratch layout would compare to the improvements they're already making. Thank you so much for listening to my thesis presentation titled Design of Efficient U.S. Shipyard Layout Material Flow Using Existing U.S. Shipyards Layout and Land Area. I will reiterate that all questions will be held until the final presentation, and I would love to welcome up my classmate, Gunnar Nee, to present his thesis. Thank you.